All right, welcome back everybody. Here we are in section 512 of AP Calculus, Exploring Behaviors of Implicit Relations, the final section of Unit 5, which pretty much concludes the differentiation portion of our course. So we're going to split this section into two videos, however long it takes us to do each one, and we're going to go through one example in each. The whole idea being that we learned about implicit differentiation back in Unit 3. We learned how to take the derivative of a function that was implicitly defined. We learned how to take the second derivative, etc., etc. In this lesson, what we're going to do is we're going to look at some AP-style problems that utilize implicit relationships and look at some of the things that they might ask us to do on an AP exam using our understanding of implicit functions and the calculus related to them. So here we are, example 1. This is actually free response number 5, which is a non-calculator question from the 2021 AP Calc AB exam. So a very recent free response question for us to look at here. So my opening prompt, consider the function y equals f of x, whose curve is given by the equation 2y squared minus 6 equals y times the sine of x for y greater than 0. I feel like that y greater than 0 might come into play at some point in time. So anyway, here we are. The first part asks us to show that the derivative of this function is equal to y cosine of x over the quantity 4y minus sine of x. A lot of times on these implicit relations questions, they will have you start with a verification of the derivative, and there's a major reason why they do that, and that is to make the grading not as ugly for the graders, because we want everybody working with the same derivative on parts B, C, and D. We're going to be using that same derivative, and if people make an error in coming up with the derivation of dy dx, it can make the whole problem a really ugly mess to slog through. So we start with the verification, and that way we can use this dy dx in later parts of the problem, even if we're not capable of taking the derivative to get there. But we are capable of taking the derivative to get there. So let's go ahead and take the derivative of 2y squared minus 6 equals y sine of x. So on the left-hand side, the derivative of 2y squared, that's going to be 4y times the derivative of the inside, which is dy dx. We're differentiating with respect to x because we're trying to find dy dx. The derivative of minus 6 is 0. And then the derivative of y sine of x, I need to use the product rule. So I've got y times the derivative of sine of x plus sine of x times the derivative of y, which is dy dx. I now want to group all of my dy dx terms together on one side of the equation. So I'm going to go ahead and subtract sine of x dy dx from both sides. And I'm going to leave the y cosine of x exactly as it is because I see in my verification that I do indeed want that. So there's no need to change that. That's exactly what we want. And then we factor dy dx out of here. And we divide both sides by the quantity 4y minus sine of x, giving us dy dx equals y cosine of x over 4y minus sine of x. And you want to make sure that your algebraic manipulation takes you exactly to where they want you to be here. For instance, do not write your derivative as dy dx equals y cosine of x over negative sine of x plus 4y, or dy dx equals negative y cosine of x over sine of x minus 4y. You want to derive it exactly to the form that they've given you in the problem to derive it to. So here we go. All right, so we're done with part A. Part B. Write an equation for the line tangent to the curve at the point 0, square root of 3. So in order to write a tangent line, we need two things to write the tangent line to a curve at a point. We need the point, and we need the slope of the tangent line at that point, which we're going to get by evaluating the derivative at the point of tangency. So we want to find the value of dy dx at the point 0, square root of 3. And so we're going to go ahead and do that. We'll substitute square root of 3 in here for y, and 0 in here for x. That's 4 times the square root of 3 minus the sine of 0. And we've got to calculate some trig values here. Cosine of 0 is 1, sine of 0 is 0, so this all simplifies to square root of 3 over 4 square root of 3, which further simplifies to 1/4. And now I have my slope of my tangent line and I have my point of tangency. I've got two options here. Since this is the y-intercept, I could just use slope-intercept form. I typically just go ahead and plow forward with point slope. Got y minus the y coordinate is equal to the slope times the quantity x minus the x coordinate, which I can simplify to this. It's a totally good answer. Or I could simplify to this. Don't forget your plus sign, like I did. Or I could simplify to this. And actually, any of these three are going to be acceptable answers for our equation for our line of tangency there. Okay? All right. Let's see what part C has to offer. Part C, for x between 0 and pi and y greater than 0, find the coordinates of the point where the line tangent to the curve is horizontal. Okay, in order for a tangent line to be horizontal, that means that it has a slope of 0. And therefore, in order for the slope to be 0, we need the derivative's numerator to be equal to 0 and the denominator not to be equal to 0. So we're going to start by setting the numerator here equal to 0. Y cosine of x has to be equal to 0. And of course, this is where that y is greater than 0 comes in being important for us. Since y is greater than 0, we know that y is not equal to, oh, I don't know if you guys can hear those sirens in the background. I don't know if you can, but y is greater than 0. So this is not equal to 0. And so my solution for this is going to be when cosine of x is equal to 0. And I'm going to find the x value between 0 and pi that makes that true. And that leads to an x value of pi over 2. Okay, that's the x coordinate of the point where the tangent line to the curve is horizontal. Now, we're looking for a point, not just the x coordinate, but both of the coordinates of the point. And so we're going to substitute pi over 2 back into the original function for x. And when we do that, that gives us 2y squared minus 6 is equal to y times the sine of pi over 2, which is just 1, is equal to y. And so 2y squared minus y minus 6 is equal to 0. That's 2y and y. And if we factor that, let's see, that's plus 3 minus 2. That works. And so y equals negative 2 or negative 3 halves, or y equals 2. Now remember, y is greater than 0, so we're going to rule out that one. And therefore y equals 2 is our y coordinate of the point where the line tangent to the curve is horizontal. And so I've got my x coordinate and my y coordinate, and there's my point where the line tangent to the curve is horizontal. Okay, and one last thing. Determine whether f has a relative minimum, a relative maximum, or neither at the point found in part C. Justify your answer. Part D here is a spot where the second derivative test is crucial for us, because when we have an implicit relation, we can't just make a sign chart like we can for an explicit relation. So it's impossible for us to use the first derivative test to determine whether this is a relative minimum, a relative maximum, or neither. So we're going to have to use the second derivative test. And so we're going to have to take the second derivative of this function. So we take the derivative of dy dx. So d squared y dx squared is equal to, and so I've got low, 4y minus sine of x, times the derivative of high, negative y sine of x, plus cosine of x dy dx. So there's low d high minus high d low, which is going to be 4 dy dx minus cosine of x is the derivative of our denominator. Square the bottom, and away we go. 4y minus sine of x, quantity squared. All right, now we're determining whether this has a relative minimum, a relative maximum, or neither at the point found in part C. At the point found in part C, the x-coordinate is pi over 2, the y-coordinate is 2, and the derivative, since the line tangent to the curve is horizontal, that means dy dx is equal to 0. So if I evaluate this second derivative at this point, I'm going to just substitute all of these values into the second derivative equation. So 4y, so that's going to be 8 minus the sine of pi over 2 is 1, minus y times the sine of pi over 2, which is again 1, plus the cosine of pi over 2, which is 0, times dy dx, which is 0, minus y times the cosine of x, which is 0. So this doesn't even matter because that's just going to be 0. Okay, all over 4 times y, which is 2, minus the sine of pi over 2, which is 1. Come on. All of that quantity squared. And when we simplify this, we end up with negative 14 over 49, which reduces to negative 2/7. Okay, so f has a relative maximum because the curve here is concave down, has a relative maximum at pi over 2 comma 2 because dy dx equals 0 and d squared y dx squared is less than 0. Probably should have added the phrase by the second derivative test. All right, and there is that problem. Okay, now just to kind of show you some things really quick, I'm going to pull up my Desmos here, and if I typed this original function in here, 2y squared minus 6 equals y sine of x. Okay, looks like that. We're talking about when y is greater than 0, so we're talking about this upper curve here. Oops. We're talking only about the upper portion. Okay, now we wrote an equation for the that was tangent to the curve at the point 0 comma square root of 3. If you remember what that equation was, it was y equals 1/4 x plus the square root, oops, double oops, 1/4 x plus the square root of 3. You see that's the point of tangency here at the intercept. And then later on we said, hey, where's the line tangent to the curve is horizontal? That happened here at pi over 2 comma 2, which is this point right here. That's pi over 2 comma 2 is a place where we've got a horizontal tangent between 0 and pi. All right, and you can see that that is indeed a relative maximum, which verifies part D. So a whole lot of things to piece together here. Very cool kind of problem for us, and dealing with implicit relations is kind of a little bit more difficult. It's nice that we have the capabilities with Desmos to kind of back ourselves up graphically. All right, that takes us to the end of this lesson. We're going to come back for one more video this unit. We're going to do one more example of an AP style problem involving implicit relations. So we'll see you then. Have a great rest of your day and enjoy yourself.